Okay. Hello everyone. Welcome back to the Bangalore Theory Seminar Series. Today we have Prahlad Narasimhan as a speaker. Prahlad is a PhD student in the Applied Mathematics and Statistics Department at SUNY, Stony Brook. Prior to this, he got his MSc and BSc degrees from IISc Bhubaneswar. His main interests are in computational geometry, graph theory, and parameterized complexity. Today he'll be talking about covering partitioning and searching polygons. So let's hand it over to Prahlad.
So thanks everyone for inviting me to Bangalore. I'm here for a month and it's fun to take a week off, about 3-4 days off to come here. So right off the bat, I'm very jealous of your campus. It's very, very pretty. As I said, I'm going to be talking about covering partitioning and searching polygons, or what I like to call protecting polygonal environments. So let's get started right away. So I see protecting polygonal environments as two different kind of things, right? So one is that you can be preventive in that you can stop bad stuff from happening before they do, or reparative in the sense that once something bad happens or your environment has been compromised, you need to do something about it. So when we have something preventive, you would essentially just like to guard the polygon, right? So this is one of the most fundamental problems in CG, which is the art gallery problem. So when you want to guard the polygon, you can do it in two ways, right? The first way is to say that you want to cover it with, let's say, some nice pieces. Let's see. Weird. Okay. So you want to cover it with, nice pieces, or you might also instead want to partition it, right? With nice pieces. So these are two things that you can do. What do I mean by nice? So by nice, for example, in art gallery, you want to cover it with star-shaped polygons, right? But you might want to do it with other types. For example, convex polygons, or rectangles, or squares, or small polygons, and so on. So you might also instead want to partition it. So just so that people don't fight over the same space, somehow you want to make sure that the pieces that you're using to cover the polygon are interior disjoint. So those are two things you can do. And this is the first problem that we study. And this is the second one. I'll talk a little more about this later. The second one, which is the reparative thing that I was talking about, which is once your polygonal environment has been compromised, what do you do? So you'd want to find the target, right? So you might want to do this. Well, there are several settings. The robot that you're using might be have imperfect sensors, for example, or the target might be moving. It might be evading, or it might just be drifting, and so on. So there are several things that we can talk about here. But what I will be talking about today, very briefly, is when you have an immobile target. So it came in and it just sat around, and you have an imperfect sensor. So this is the third problem that I'll be talking about. I'm going to spend close to maybe 75% of the time on the very first one, which is covering it with convex pieces, and a little bit of time on the second and third problem, just to introduce you guys to the problem itself. So all of this is with co-authors, several of them. Here's the list. So Joe's my advisor, Joe Mitchell, from Stony Brook. So he's worked on all these problems. Valentin Polischuk is from prior student of Joe, but he's currently in Linköping in Sweden. Lynn and Keen are students of Joe. Nilanjan is in the mechanical department in Stony Brook, and Riley, who kind of headed the first paper, he actually gave this talk at Fox. He just finished his master's. He's joining Dartmouth for his PhD. So let's get started. Few general things. Please feel free to interrupt me whenever. And second, as I was talking before about this, I'm going to be writing some stuff down. I'd like, instead of using slides, I'd like your feedback on this. It's the first time I'm trying this on an actual talk. If you have any thoughts on how I can improve this style, I'd love to hear it. So with that, all that out of the way, let's get actually started with the CG. So this particular paper, which we call approximation of the convex cover and hidden set or something like that, we published this at Fox 23, so last year, and Riley, Joe, and Val. So the setting is that we have a simple polygon P, and we would like to cover it, right? So here's the definition of a cover. It's simply a set of subsets of, or a collection of subsets of P, whose union is just the entire polygon, right? So if we want to talk about a convex cover, then that is simply that for all I, your Ci is convex. So also just a quick note, because the union is equal to P, you have that each of the Ci is a subset of P, right? So you can't take a large rectangle and just place it on top of the polygon and say that you've covered it, because we don't have P to be a subset of the union. We have it to be equal to the union. So this is the definition of a convex cover. I'll define the problem explicitly in a moment, but let's look at an example first to understand the difference between a cover and a partition. So if we take a look at this figure on the left, I mean both of them are the same, but if we take a look at this one, so we can actually cover this with just two pieces, right? So if you take all the even, I guess, things. Okay, this is weird. Okay, let's see if I can handle this, because for some reason the screen isn't working as I would like it to. So yeah, so all the even ones form one cover, while all the odd ones form the other cover. So let me try to draw this properly. Right, so you have this one and the other one in red. So you can cover this with two things, right? That's the takeaway. But if you want to partition this instead, by which I mean that you want the sets that you are using to cover to be interior disjoint, then you need almost n many, right? Order n, and that is the big difference between covering and partitioning, and also why covering is in general usually harder than partitioning is. So here again, if you have this is going to be interesting. If you have something like this, now for each of these triangles that are jutting out, you need extra pieces, right? So you need about n over 2 pieces. So therefore, the takeaway essentially is that you have an order n difference in the number of pieces that you need to cover and partition stuff. So with that out of the way, let's define the problem. One thing I really like about this problem is that it's very easy to define. It's a very natural problem, and only required like 5 minutes to get to the problem definition. So you're given a simple polygon and a natural number k. Is there a k-sized convex cover of P? So can you give me k convex subsets of P which cover P? Right. So this is the problem. Let's state it again and look at what we know about the problem. So it's been studied for close to 50 years now. The first result that I've stated, the complexity theory result of NP hardness in FoCS 88 is actually not the first paper that talks about it. I think the first paper is in the 60s, but they use it for other things. They don't really talk about complexity stuff. So yeah, so it's been studied for a while. We know that it's hard, and then they raise the question of is it NP complete? But very recently, a couple of years back, Michael Abrahamson proved in FoCS 21 that it is actually existential R complete, which just means that it is equivalent to solving or equivalent to figuring out if a set of inequations with integer coefficients has a polynomial solution or not. Sorry, if it has a real solution or not. So that's for the complexity part of things. So what about the approximability? For approximability, we know that there is a log n approximation that comes from, yeah, please. Yeah, so you have a set of inequations with integer coefficients. What you want to figure out is if the question that you're asking is there rational answer which satisfies all of these inequations or not? So, sorry? No. I'm not very comfortable in existential R completeness. Yeah. So yeah, so I must confess that I'm not very comfortable in existential R questions. Yeah, all I know is kind of like the definition, and that's about it. So yeah, right. So right. The next one that I want to talk about was the approximability, or what we know about the approximability prior to our result, is that there's a log n approximation based on essentially set cover. And that runs in n power 29-ish time, so horrible running time. And we also know that there is no p-task for this. So there's an APX hardness in the same paper, IISc 2001 by Eidenbenz and Widmeyer. So our result is the first constant factor approximation for this problem. And we're particularly proud that it's a small constant. And it runs in reasonable time. The n squared running time is based on a very complicated algorithm on matching. So essentially, if you give me a bipartite matching algorithm, it'll run in bipartite matching time. So there's a very recent paper which gets n squared. If you don't want a complicated algorithm and just want to use like Ford Fulkerson, whatever, thank you. Either way, much better than n power 29. So that's our result. We also study the dual, and it becomes crucial to study the dual at the same time, which is called hidden set. Again, a very nice and easy to state problem. You have a simple polygon P, and what you need to do is to hide as many points as you can in it. So give me a set S of k many points such that no two of them see each other. Right? So if you just want to state it, this is how it is. You have a simple polygon, a natural number, and is there a k-sized hidden set of the polygon P? So very little is actually known about this problem. There is no approximation algorithm essentially prior to our work. We know that it is NP complete. This was proved in '88 by Sharma, and that it's APX hard. And this was by Eidenbenz in 2001. So what we give is a 1/8 approximation, which runs in the same time. This is the first approximation algorithm of any sort for the hidden set problem. So a few more things are known, and I think I'll briefly talk about them here. So instead of convex cover, if you want a convex partition, the problem becomes easy. It's a polynomial time. There's a polynomial time solution to it. It depends. So even if you have Steiner points, by which I mean that if you're not only using the vertices of the polygon for the covering or the elements of the cover, the sets, they don't use just the vertices. Even then, it's polynomial time. But then it becomes very complicated. It's one of Chazel's long drawn papers. And there is also a very simple thing, 4 approximation, which runs in linear time, which is taught in most introductory CG courses. So if you want to talk about convex partitioning, the problem becomes much, much simpler. And for hidden set, what has been studied was a 1/4 approximation, which runs in, I believe, quadratic time. Or maybe it's linear, I'm not sure. But that one was just for the vertices, right? So here we allow you to use whatever points you want in the polygon, while in that paper, you want to choose does there exist k many vertices which don't see each other? That's the problem that they studied. And they have a 1/4 approximation for that. So that's about what I would say for prior work. There is some stuff for polygons with holes and all that, but I think I'll save that for a little later. So I'll stop here for a moment for any questions. Exactly right. So yeah, maybe we can just draw it here. So here, for example, you can choose. I mean, here there is no reason to choose something outside of a vertex, but we have examples where you do need to do that. So here, the maximum hidden set, for example, will be 2, right? So you can choose one here, and that's a red vertex, I guess. You can choose one here and one here, but you can choose not a vertex, right? So I didn't put that in an example where you don't need to choose a vertex, but yeah, those examples do exist, and we have them in our paper. Sorry, the size of the hidden set. So right. I would think so. I think you would have something like a grid of some sort where you essentially you're forced to place stuff in the middle. So I would think that it can be arbitrarily bad. Yeah. So yeah, exactly. So yeah. So right. So that's for a quick overview of the 2 problems. I'll state the problems again in due time, so you don't need to remember it. So yeah, I wanted to say something and I completely forgot. Oh well, okay, so it'll come to me. So right, so the first thing, and this is probably the only thing that we're going to prove, is that you have the simple observation that there can be at most one hidden point in a convex polygon. So if you take a convex polygon, all I'm saying is that all 2 points, any 2 points see each other, right? So therefore, you can write down an inequality, which is essentially based on like a same as like a duality argument, right? So if you have the hidden set number of a polygon P, which is just the maximum number of hidden points, then this is less than or equal to, of course, the convex cover number of P. Which is, of course, the minimum number of convex pieces that you need to cover P. So if you take if I give you a convex cover, then you can only place one per convex piece, right? Mm-hmm. How so? Yes, yes. So so the argument is what I said, that if you give me an arbitrary convex covering, you can only place one hidden point per convex piece, right? If you place two, they see each other, therefore. So, and that's how you get this inequality, right? So so I mean, I would think that this is the dual. The convex cover minimum number of convex pieces is the dual, because you want to ensure that no two see each other, right? So which is the same as saying have a polygon where every 2 points see each other, which I believe implies that it's convex. Yeah. So if you have a set where every 2 points see each other, then I believe that that set is convex. Ah, okay. So right, right. So maximum number of visibility polygons where the polygons themselves are disjunct. It need not. I don't think it'll partition the polygon. Like as in, there might be white spaces in the middle. Right, right. And it might also not cover the entire polygon. So there might still be white spaces left. So right, so the inequality is okay. This is really the main thing that we're going to use. So here's a quick sketch of what we're going to do. I break the entire algorithm into 3 steps. So the first one is that we are going to devise approximation algorithms for what we call weakly visible polygons. You might have seen this before. They are polygons that where every point you can see from an edge, a special edge essentially. I'll define them formally down below. So why this is useful is that there is a very useful decomposition of any polygon of your choosing into weakly visible polygons. And this has been studied for a while. It's called the link distance map, but a lot of people also call it the window partition, which is a term that I prefer. So it is done as follows. So you can choose any point you like, your favorite point in the polygon. Let's say we choose this guy, right? So now what you do is just look at the visibility polygon of this one, right? So that will cut. You will have a cut here, right? So this is your first level somehow, and this is your S. Next, what you do is use this window to look at the polygon, right? Which is why it's called a window partition. And that mark all of the polygon that you can see from this particular edge, right? So that would be, I would say, something like this, right? And then repeat, right? So the next step, you would probably have something like this, and I don't know if that sees this. I think it does. Something like this, and something like this, right? So this entire thing, and then the rest you can see from these three windows, right? So notice that there's no reason for that to only be one window at one point. After a few steps, you'd almost expect there to be many windows. So here there are three, right? So right? So this particular partitioning is called it's called a window partition of the polygon. So one thing that we notice is that each of these polygons are indeed, yeah, please. Oh, yeah, sure. So a visibility polygon of a particular point is the set of all points that it sees. So if you take S, then the set of all points that it sees is this triangle.
Why the line the right side?
This one? This one?
Between these two. If you put a triangle at the top, right?
This one, right?
Why
Yeah.
is it like that and not like this?
Okay. So when we say that it can be seen through this window, what we mean is that it can be seen through any point in the window. So if you take this point, for example, that is when the triangle will look like what you said, right? So it will cut through like this. So let me try to draw it in purple. Exactly. Yeah. So if you take this point, you cut like that. But if you take this particular point, then you cut like this, right? Lying on the exact. So there's a lot of nice things about the link distance map or the window partitioning thing. One is that it can be done quickly. It can be done in quadratic time. I believe it can even be done in linear time, but I'm not sure. Don't quote me on that. Right. So once you do this, so one more thing is that these particular polygons are indeed weakly visible, and they're weakly visible from the edge which we use as the window, right? So by which I mean that every point in, for example, this red can be seen through this blue window, right? And that is essentially by definition, right? So each of these are weakly visible. One more thing that we know, and this is not something I'm going to prove, is that if you take any convex polygon, it can straddle only three pieces here. So the proof is not very hard, but just lack of time, I'm going to skip it. And one more, so what I said was that if you take any convex set, a convex polygon specifically, then it can straddle only three of these polygons. which I've used to partition. So as in, it can't intersect more than 4. Yeah, so it can intersect at most 3 polygons. Sorry? So, okay. Yeah, so it's okay, so here's what I mean. So if you take a convex piece, it can look like this. But my point is, what I'm trying to say is that it can't go through 4 polygons here. That's all. It can go through at most 3, right? It can intersect at most 3. Exactly. Yes. Exactly. Yes. Right. Yeah. I'm not sure. It might be like I'm trying to think of like a star with super tiny like star pieces, and if you choose like not the center, then it might be extremely bad. Um, so mhm. It's not clear to me. So at least for our thing, it doesn't matter. The number of cells doesn't really matter. Um, so will it help in? So essentially, the what I said about yeah. Yeah, so you lose a factor of 3, but I'm not entirely sure if you're careful about choosing your starting, maybe you can bring it down to 2 or something. That might be doable, but I'm not sure if that's been studied before. Yeah, so I'll define it in the next slide. Just give me a second and hold me accountable, please. So uh, yeah, so yeah, back to the overview, the idea is that you cover each of these guys independently. And the, the point is that when you do that, you don't lose too much, right? Like, because it's, like I said, there might be convex polygons that go through some of these. And when I try to cover only this independently, like the blue one independently, I might lose on some stuff. I could have actually extended this and covered some more of the polygon. But the claim is that even when I look at these things, these problems or these polygons independently, I don't lose too much. So um, we have a proof that you lose at most. Yeah, please. Both. So for convex cover, we lose a factor 3. For hidden set, and that's what I've written here, is that there are essentially like 4 types of cells. So these blue and reds are like odd and even levels essentially. And then you have left and right based on the window is to the left of the polygon or the right of the polygon. And essentially, there's a very simple proof that these sets are independent somehow. As in, if you take 2 polygons of the same type, then no 2 points see each other, something like that. So essentially, again, if you place hidden points independently and take the best of the 4 types, then you only lose a factor 4. So for hidden points, you lose a factor 4. For convex cover, you lose a factor 3. Okay. This is, I think, something that can possibly be improved if you want to improve the approximation factor in total. But I think this might be harder than what we have for weakly visible. We have a 2 approximation for weakly visible polygons. So that gives us the 6 approximation for general polygon because of the 3 factor, and an 8 approximation for general polygon for hidden set because of the 4 factor that we lose here. I honestly think that it's going to be easier to improve the 2 because we actually don't even have a hardness, for example, or like we haven't ruled out a p-task for weakly visible polygons. So I think it might be doable to improve this to a 3 plus epsilon or 4 plus epsilon by improving the weakly visible thing to a p-task. So we don't even know if the weakly visible thing is NP hard or not. So the NP hardness proof that they use for the general convex cover, it does not work for weakly visible polygon. So yeah. Okay, I'll finally define weakly visible polygons. So a polygon is weakly visible if you have an edge. So we'll usually we just put the edge in the bottom and have it whatever parallel to the x-axis. Doesn't really matter. So it's weakly visible from this yellow edge if every point in this polygon can be seen by some point in the yellow edge, right? So if you have this point here, just a second. Yeah. So if you have this point here, then there exists some point that sees it. That's all I care about. Okay. So we actually impose an extra condition on this and say that we don't want something to look like this. Like, I mean, this is still weakly visible. So again, my screen has shrunk for some reason, so I can't. Yeah, so this is technically still weakly visible from this edge, but one more good thing about this link distance map is that it doesn't give us polygons like this. It only gives us polygons where it's convex on the ends, so we only consider those kinds. So we don't really care about this thing. Oh, so I just mean that these two angles are convex. So right. So now let's look at this particular object. Mm-hmm. Oh yes, yes. Yes, 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 yes. Yeah, that's exactly right. Well, I guess you could have some weird degenerate cases where it's only visible from a vertex or something like that. But yeah, like if you have, but yeah. So if you forget about those weird edge cases, then I guess they're the same. So here's another observation that we'll prove mostly by figure. So it's the following. It says that if you have 2 points, A and B, which lie below the curve, which is this one, right? So C of AB is the curve above A and B. So whatever, you order points clockwise, anti-clockwise, clockwise, whatever. The definition that makes sense. So in that particular case, you see that A sees B, and the curve lies above it. So it's the fact is that the converse is also true. That if the curve lies above AB, then A sees B. So essentially, what I'm saying is that it can't be the case that something after this, so you can't have something like this come and interrupt A seeing B. Why is that? Well, that's because if you take this particular point, this has to be weakly visible from the yellow edge. And if it interrupts A seeing B, then it won't be, right? Because everything, stuff that it sees will be above A, and the yellow thing is below A. So that's the proof of this particular observation. So here's a definition that we'll have. We're going to define a post set, right? A partially ordered set. So we have edges E1 through however many, which are everything in this polygon ordered this way around. So you have E1, E2, E3, so on. So we say that EI is less than or equal to EJ, just a relation. If I is less than or equal to J, so as in it comes before the other edge. And moreover, EI strongly sees EJ, not weakly, right? So when we had weak visibility, we said that two things. So this edge weakly sees that edge if every point in the other edge can be seen by some point in the first edge. For strong visibility, we need every point to be seen by every point. Okay. So for example, here, So for example, here we could have this edge. Let me choose the highlighter. You could have this edge and this edge, which strongly see each other. Right. So let me see if So these two strongly see each other, right? So every point in this sees every point in that. But if I take a look at just a second. If I take a look at these two, these do not strongly see each other, but they're like some of this sees some of that, right? Indeed, some of this sees all of this, but there are points which don't see each other in these two sets. So we would not say that these strongly see each other. Okay, so if that is good, the relation is the following: that EI is related to EJ if I is less than J, and EI strongly sees EJ. The next, okay, let me remove the red ones so that we only have the yellow ones to worry about. So the next lemma follows actually directly from this observation, is that if that's essentially the transitive property, right? If EI is less than EJ and EJ is less than EK, then my claim is that EI is less than EK, right? So what you expect happens is essentially all I'm saying. So so if you take these two, right? So we have a relation between these two sets, right? This is your EI, this is your EJ, and this is your EK. If EI sees EJ, strongly sees EJ, and EJ strongly sees EK, my claim is that EI strongly sees EK, right? So the proof of this actually follows from here. So when you have EI strongly seeing EJ, we have something like this, right? So we know that this curve from here to here lies above this convex polygon. And because of this relation, EJ and EK, we have that this curve lies above this polygon. And therefore, this entire curve lies above this polygon, which gives us the convex, which gives us the transitive relation. So that's the lemma. So now we can define a directed graph, right? So you have a graph G where the vertices are the edges of the polygon, except this weakly visible edge, the main edge in the bottom. and you have an arc between two edges, two elements of this vertex set, if they are related through this four-set relation. So, great question. Let me, yeah, I was going to bring that up. So if you take, okay, let's try to draw it in blue, right? If you take this guy and this guy, so you have this strongly sees this, but this also strongly sees this, I think. Yeah, so you have to be a little bit careful. Assume that this is slightly above. So you have that EI strongly sees EJ and EJ strongly sees EL, let's say. But you have the fact that you have EI is less than or equal to EJ, but you have EL is less than or equal to EJ. So this doesn't, so EI doesn't strongly see EL though, right? So this is exactly why we have the ordered relation and why we have a DAG. If this didn't happen, the algorithm would be much easier. I mean, it's still, I would still consider it simple, but if this didn't happen, then essentially G becomes Cordell and all that, and then you can run fairly easy quadratic algorithms. Instead, now you have to run a complicated quadratic algorithm or an easy cubic algorithm. So yeah, great question. Okay, so the corollary is the following: that if you have a path in the graph, then you have a convex subpolygon of P, right? So which is exactly what I said here. So let me erase all of these so that we have some space. So if I have EI, EJ, and EK, the claim is that we have a convex subpolygon. So here it is. It's exactly essentially the convex hull of these two edges, right? So this is my convex polygon, right? So if you have a path, you have a convex polygon here. So therefore, oh, I could have drawn it here. Never mind. So so a path in G corresponds to a convex subpolygon in P. And therefore, we would expect a path cover in G to correspond to a convex cover in P. Unfortunately, the math gods don't like us, and that doesn't happen. So here's a path cover of the graph. So you have 5. Clearly, it doesn't cover the polygon. But thankfully, this is still salvageable. So you can append a few points. So this in particular is the following. So if you take the rightmost point that sees this base, so that would be this one somewhere here, and the leftmost point that sees this, and if you extend those things, then you get this triangle that you append to this. So we are not adding an extra polygon, right? We are just appending a polygon to this. But unfortunately, that still doesn't cover the entire polygon. There's a lot of white spaces. So we add an extra polygon, which is the green one. So you take one point, and then the leftmost point and the rightmost point of the weakly visible edge that sees it, you get a triangle. Unfortunately, what remains is not convex anymore. So you're adding essentially an extra polygon. So if you have a path cover of size k, we are going to have a convex cover of size 2k, right? Which is the key takeaway that I have below. So, there's also a proof that this indeed works. So if you add this green and the blue triangles for each of these polygons, then the claim is that you cover all of it. The proof is not too hard, but due to lack of time, I'll skip it. So yes, for each path in the cover, you have 2 polygons. So the blue one you can essentially append to the red one and still make sure that it's convex. The green one, we couldn't figure out how to do it. Maybe there is a way. We also gave examples where even if you maximally extend each of these red polygons, instead of doing this blue-green thing, you still don't cover it, unfortunately. That would have been great, but we couldn't make it work. Maybe there's a way to choose a good path cover, a good optimal path cover. And if you extend that optimally or something like that, you get to cover the entire polygon. But we weren't able to do that. If you are, then you improve everything by 2. Yeah. Right. So here's the key takeaway, that if you have a k-sized path cover of G, then there's a 2k-sized convex cover of P. Of course, here P is a weakly visible polygon, right? So there's a very old theorem. It's from 1950, so I think I can say it's old without offending anyone. It says that the optimal path cover is equal to the independence number of directed graph. So the independence number, again, is just 2 things that don't have an edge between them, right? So what is the maximum number of points that you can take? So note that therefore a path cover, we said that this corresponds to somehow a convex cover, and we'll show that this corresponds to the hidden set, right? Edges that don't sorry, as I said, my screen has shrunk for some reason, so I have to zoom out a bit. So right, so we'll say that the independence number, if edges don't strongly see each other, then we show that you can actually place points where none of them see each other, right? So again, the proof is going to be by picture. Let me draw. Oops, let me draw. A bunch of points, a bunch of edges that don't strongly see each other. Here they are. What else? This one possibly, and then maybe finally this one, right? So again, like I mentioned, these 2 guys, they don't strongly see each other, but they do. I think, yeah, some of them see some points, which we say it's okay. So this is an independent set of the graph, right? Because there are no edges between these edges, right? There are no arcs between these edges in our graph. So it turns out that we can indeed place hidden points in here. This is a little non-trivial because essentially the idea is that you place it super close to the endpoints of these edges. But we unfortunately have to define super close properly. So essentially we extend all edges, and push stuff very close to the endpoint. That's kind of the idea. So essentially it turns out that you can place these hidden points very close to the endpoint of the edge. Right? So of course you need to be careful because, for example, you couldn't have placed this here, right? And then they wouldn't it wouldn't be a hidden set anymore. Okay, so we have a proof that you can indeed do this, right? That's the key takeaway here, which is that if you have a k-sized independent set of the graph G, then you have a k-sized hidden set in P. And sorry. Oh yeah, sorry. Yeah, that's a great question that I forgot to mention. So it turns out that you can do this very quickly. Dilworth's theorem is actually iterative in some sense, and it somehow reduces to finding a matching in a bipartite graph. So this is, if I remember right, an exercise in the very first chapter or in CLRS. Yeah, so it is well known that you can reduce it to a bipartite matching problem, and this is where our complexity comes from. N cubed, if you just want to use for Fulkerson, yeah, please. I have 5 minutes. Okay. So N squared, if you want to use something fancy that was in FoCS 23. So point is quickly. If there is a k-sized independent set, there is a k-sized hidden set of P, right? We're going to use these two things to get our approximation factor, right? And what we're going to do is to use what we wrote before, which is that the hidden set number is at most the convex cover number, right? So this is the first thing that we proved. Indeed, the only thing that we proved. So what we have is we've given a k-sized hidden set, which means that the hidden set number is at least k. We've given a convex cover, which is of size 2k, which therefore means that the convex cover number, which is the minimum, is at most 2k, right? So if I report k as my hidden set number, then I am off by a factor of at most 2, right? So because the hidden set number is at most 2k, and it's at least k. So I'll report k. For the convex cover number, I'll report 2k. And we know that you're again off by a factor of at most 2 because it's bounded below by k, right? So therefore, we have a 2 approximate convex cover and a half approximate hidden set, right? Again, 2 half just because it's a maximization minimization thing. So therefore, in quadratic time, you can find these 2 approximate convex cover for weakly visible polygons. And because this window partitioning and all that can be done quickly, we have a 6 approximate convex cover and a 1/8 approximate hidden set in general simple polygons in quadratic time. So I guess I'm about done. I think the other problems that I had, I only had like mostly figures in them. I will talk about that later over lunch or something like that. I'd only essentially defined those problems and not given any solutions as such. These two are still unpublished work. So I'll end here with a slide on this key takeaways. And thank you again. I have a minute. So thank you for coming and inviting me again. Thanks. No, I don't think we found it for weakly visible polygons. So yeah, it would be interesting. Again, we haven't even proved hardness. So for all we know, there might be a, even if it's complicated, an algorithm in polynomial time for weakly visible polygons. Yeah. Yeah, exactly. Yeah. 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 Mm-hmm. all possible polygons. All possible. Say that class finds that because we are essentially solving MIS in good way, right? For that. So which means the graph class has to have some structure. So let me see. Yeah. So the graph class that we have. The one thing that we proved is that its own transitive closure, in the sense that like the relation that I said, right? And I think for that we know that it's easy to find the independence number. So yeah. Oh yeah, sure. So yeah, so the blue triangle. Let me erase this. So so if you take a polygon that we've constructed using this path, right? You have the base, right, which is this heavy purple line. What you do is look at the leftmost point that the right side of the base sees, and the rightmost point that the left side of the base sees. It turns out that these two, if you join them, it turns out that they do intersect. We have a small proof with a couple of lines. And then this forms a triangle, right, with the base. So you append that to the base. In this case, it actually, if you take the entire thing, it won't remain convex anymore. So you only take it until it's convex. So here, we believe that the rightmost thing is this one, and the leftmost thing is that one. So, oh no, I think it might. Yeah, so essentially it might not remain convex anymore because of these edges here. And if that is the case, make sure that it is convex. Well, I mean, I guess I'm not sure what the nice answer is, but essentially this worked. So what we wanted was a nice way to say that maximally extend convex the convex polygons, right? So we are given this, and I want to extend it so that it still remains convex. We weren't entirely sure how to do that in general, so we wanted to append something to the polygon so that it still remains convex. And the easiest way we found was I mean, it doesn't really matter if it does, because we are essentially still going to bound it by the number of paths, right? So here the number of paths was 5, and we would bound it by that anyway. So if there's a way to maximally extend these polygons and cover the entire polygon, then that would be great. So we weren't entirely sure how to do that quickly. This, of course, can be done in whatever linear time, right? So can't we add a parallel, the thick purple and add a parallel outside the polygon? So outside the polygon? Like just extend the parallel line outside the base of the polygon. Right. And then like no, parallel to the same angle. Oh, like this? Yeah. Maybe even right. And join the so, and then whatever, intersect it with the polygon itself, because I mean you want stuff to be like a subset of the polygon, right? The cover, all the elements of the cover should be subset of the polygon. But I do think that this might work. So the big problem, of course, is that if you do this, now this is not convex anymore. This is a reflex vertex. So you can at most only extend up to this. and same thing here. So you can only at most extend up to that, right? So of course you can maximally extend on the other side even, maybe, like for example you could do something like this. So but yeah, so like I said, there's an example in the paper where even when you maximally extend, it doesn't cover all of the polygons. Yeah. But yeah, I mean, these kind of things could work. Maybe you wouldn't need extra stuff anymore. And if you do, you, as I said, reduce the factor by 2.